want to use our data to update the parameters of the Gaussian process. And we will try to achieve this goal with kernelized linear ridge regression. So this is our notation. We have a training set D, which has x, I, y, I input-output pairs. If we just do linear regression after, say, a feature map phi, then this is the equation of the linear regression. F of x is just the inner product between w and phi of x. And in linear regression, our goal is to find a w, say w hat, that minimizes this cost function. We have n input-output pairs. Okay? Raise your hand when you get lost. There will be lots of calculations today. Quite often, we don't just do this. We want to regularize this cost function with a so-called ridge term, and that then we call this ridge regression. So it turns out, we will see that later, that Gaussian process is just a kernelized version of this. Okay, so let's see how we get to that. So again, notation, capital D is our training set. We have n input-output pairs. Xi is the input, yi is the output. And we collect the inputs into a design matrix. It's called, the collection of inputs is called design. So X is x1, xn is a capital D times n matrix, and the outputs y is just y1, yn. Okay, so this is our training data. And if we just do linear regression, then f of x is x transpose w. That will be our regression, and we assume that our observation is noisy. That is, y is, say, f of x plus some epsilon. So in other words, this is x transpose w plus epsilon. And for this epsilon, we assume that it's a Gaussian, it comes from a Gaussian distribution with some variance sigma squared. Our goal is that we have this input-output pairs, and we want to find the best w, right? So we do that with maximum likelihood estimation. Then the likelihood function, that's the probability of y is given x and w, will be, because we assume that the input-output pairs are independent from each other, that is, we have IID data, it would be just the product of these terms. And then, so that would be just the maximum likelihood estimation. And then we do an extra assumption that we assume that on the w weights, we just don't just do a maximum likelihood estimation, we assume that we have a Bayesian prior distribution on the w's. Okay, so we will assume that we have this Gaussian distribution on w's, and we want to calculate the posterior distribution of w's after observing the data. You start with this prior distribution on w. You observe the data, x and y's, and we want to calculate the posterior distribution of w's. Okay? So if so that will be the posterior distribution. So let's see the likelihood distribution. That's the probability of y given x and the w's. We have n independent pairs, and we know that for each the distribution of yi given x and w, the distribution of y given x and w will be just a Gaussian distribution, right, with this mean and covariance sigma squared. So the probability of y given the input x and the weight w will be just a Gaussian distribution at yi with mean xi transpose w and sigma squared. Okay, so in other words, so this notation is just a density of a Gaussian distribution at this location with this mean and this variance. Okay, so this is just the density function, and I can move these terms into a vector matrix notation. So using these notations that we had before, y is this vector, x is this design matrix, then we got that this likelihood function will be just the squared L2 norm of the y vectors minus x design matrix transposed the w weights. Okay, in other words, this is just the density of a Gaussian distribution at location y with mean x transpose w and with this variance. So if I just want to do a maximum likelihood estimation on this, then I just need to maximize this in w.
So it's the same like regular linear regression?
It's exactly, it's just a linear regression. So the maximum, in this case, the maximum likelihood estimation and the linear regression is the same, as you said, because what we have is we just need to maximize this. All right. So linear regression and maximum likelihood estimation in this case is the same. So now we do something different. That we also assume that on this W we have a Gaussian prior distribution. Okay. So say W is sampled from a Gaussian distribution with mean 0 and covariance matrix says sigma, and we are in a p-dimensional space, so I just use sigma p. All right. So let's calculate the posterior distribution of W after that. So the posterior distribution would be just the product of the likelihood. We calculated this, multiplied with the prior and divided with this term. All right, so this is just the base rule. This term doesn't have W in it, so we can just say that this probability of W given x and y is proportional to the product of this term and this term. We already calculated this term, that's this Gaussian distribution. And on this term, we assume it's a Gaussian with 0 mean, covariance matrix sigma. Okay, so here is my question. If you look at this, what kind of distribution it will be in W? Right? So this is a distribution in W. We can see that it's a product of two Gaussians. What kind of distribution is it in W? Gaussian. Okay, so why is that?
It's a quadratic function, the exponent.
Right, so it's there's a quadratic function inside the exponential here. There's another quadratic function inside the exponential here. So if I multiply these two guys, then it will be a quadratic plus quadratic inside the exponential function, and the quadratic plus quadratic is a quadratic. Okay, so let's see the details of that. So this is where things get a bit ugly when we calculate the details of this. So this is the posterior distribution, is proportional, as we discussed. The product of this Gaussian distribution, the likelihood, multiplied with the prior. And the first Gaussian distribution is this. The second Gaussian distribution is this. And now, it turns out that you can rewrite this expression as this quadratic expression. So it's a quadratic in W, where I introduced two new notations, W bar and A. So W bar is defined by this expression, A is defined by this expression, and then we can see that this posterior distribution will be, as you see here, a Gaussian distribution with mean W bar and covariance matrix A inverse, where A is defined by this. Okay, so to prove it, it would be a few minutes of calculations. So let's keep that. But I want to know that all of you would be able to prove this, that this expression equals this expression. So who thinks that if you go home, then you couldn't prove this? So this trick is called completing the square. When there's a quadratic expression and you want to rewrite that quadratic so you want to rewrite this as a quadratic expression in W. And this is how you would rewrite to see that this is the mean of the new Gaussian distribution, this is the covariance matrix of that Gaussian distribution. So you just need to collect the terms. Okay, so...
Does the mean actually change? I mean, if you multiply two Gaussians and
so this was the
0, so why does it change the...
So what was... This was the mean of distribution Y. This is a mean on distribution W. So these are different means, right? And then you observe Y that updates the mean for W. So, for example, very extreme case, say this was just Y, this was just W here, and there was the sigma was 0, okay? It means that Y is the same as W. If you observe Y, then in the posterior, the new mean would be Y, right? So if you observe some data, that should update the mean. And this is what we see here, that will be the new mean. And as you see, it depends on Y. So when we observe data and we update the parameters for W, that should depend on Y's. And of course, it depends on our observed X as well. Okay, so bottom line here, that's important to know that in the posterior distribution, this will be the new mean. And this will be the new variance. And one very strange property of the Gaussian distribution, that this variance does not depend on Y. So it doesn't matter what you observe. The variance of the posterior distribution will be independent of the Y's. It doesn't matter that in the regression you observe large values or small values. All that matters is the locations and how many variables you observe.
Is it the variance or inverse of variance?
So this will be the covariance. So this is called precision matrix, and the inverse of this is the covariance.
The expression there, it's like an exponent, right? So you use this.
Right. So the inverse of this is the covariance matrix. Yes.
Can you give any intuition why this is the case? Why, like, it doesn't depend on Y?
For Gaussian, so the Gaussian distribution is like that. So what happens in the posterior distribution? You got a new mean and you got a new variance, right? So the posterior distribution will be Gaussian. We discussed that. It will have a new mean and it will have a new variance. And it turns out that this new variance actually just depends on how many observations you had, not what you observe. So it's very similar, for example, when you say you just had a bunch of IID variables and you want to calculate say I had x1, xn, and I calculate the mean of this. It will be 1 over sum of xi. Then the variance of this quantity will depend only the number of observations of n and the variance of this, but not actually these values. So the new variance depends on the variance of the original quantities and how many observations we had. And that's what happens here with Gaussian distributions, that the posterior variance just depends on how many observations we had. The more observations we had, the smaller the variance will be. But it doesn't matter whether you observe large values or small values. But that's just true for Gaussian distributions. For other processes, it's not necessarily true. Okay? Yes?
That's the variance of W, right? Not the variance of F.
Exactly. That's just the variance of W.
Still, its distribution is not independent of y anyway, right? Because the mean depends on...
The mean depends on y.
So distribution, the posterior depends on...
It depends on y, but only the mean,
Only the mean.
not the variance.
Maybe higher moments too? So it cannot be...
No, only the mean. So with Gaussian, we know that it's a Gaussian distribution, and the Gaussian distribution is characterized by its mean and variance, and then you are done. Maybe just another note on this. Hope it will not be more confusing. That's why it makes not easy to use Gaussian processes in active learning. So in active learning, what you want to select the next input points that would minimize your variance the most. But in this case, it's a bit weird that all the variances would be independent of the observations, right? And then how would you do active learning if that's independent of your observations? All right, but that's just a side note.
But it does depend on the variance of the axis.
Of the axis, yes, but not what you observe. So you have the axis, that's the inputs, right? But it doesn't depend on the observations. So it's like before you observe something, you would know what to do. And in active learning, we like to do that. You choose a location, you want to observe something, and based on what you observe, you want to make decision what to do next, right? But here, it's independent of your observations. But you are right that indeed it depends on the locations, the inputs. All right, and so there was a note here that we don't really care about the distribution of W. What we care about is the distribution of my prediction. And we do linear regression. So if I have a distribution for W, already we calculated that posterior distribution, my prediction for F, that would be X transpose W, right? And what's the distribution of X transpose W if I already know the distribution of W is a Gaussian? So it will be a Gaussian. What will be the mean?
XT mean of W?
Right, so the mean will be the mean of W, which was W bar, times X transpose. That will be the new mean. And what will be the variance? So it will be X transpose times the covariance of the Gaussian times X. Right? So this is what happens here. If on the posterior distribution of W had mean W bar and covariance matrix A inverse, then in the predictive distribution, that will be a Gaussian distribution with mean X. So I want to predict the distribution at the location X star here. So that will be a Gaussian distribution with mean X star transpose W bar and with this covariance matrix. Yes?
What do you mean by writing F star over there? I mean, in what sense it's a random variable?
Right. So what I was curious about is we calculated the posterior distribution of W, and I want to use that to predict the function value at the location X star. So you fix your location X star. You had your training data, you learned W, and I want to do that use that to do prediction at any location, say at the location x star. So x star is a fixed quantity here. You choose an x star and you want to predict the function value there.
No, I said f star. I mean,
So f star, right? So
down there in the integral, I'm just trying to understand in what sense it's a random variable.
So f. In this case, it's not. So it's but what you might. So how about this? That it would be probability of y given x star and w. Then it's a random variable, right? So that's why I just use this delta function. So this thing, if the probability of f star given x star and w, this is 1 if f star is x star transpose w and 0 otherwise. So that's the notation, yes?
So now I've gotten a bit confused.
Mhm.
Isn't w a random variable?
W, right, so
So x transpose w will be a random variable in this case. You just
right, so it's I'm calculating the probability of this given w. So w is given, so it's fixed. So that's why so it's a fixed w. In a fixed w, this is this quantity, but of course, then we will have a distribution on w, and that's the distribution of w. But when w is fixed, then it's just what's f star given x star and w, and that's just x star transpose w. Does it make sense this way? So in other words, just look at this. So it's the probability of my prediction. So my prediction will be a random variable. And the location is x star given x, the observed data, and y observed label. So this is my training data. At any given x star, I want to predict the Gaussian distribution for my prediction, and that will be this Gaussian distribution, which has this mean and this variance. That's all I want to say. Does it make sense? Yes?
We assume at the beginning that epsilon was some normal. If it's normal, then so are we just ignoring epsilon there because otherwise it wouldn't be the delta, but some distribution respecting.
Right. So here I ignored. So that's why this confusion comes from. That here I just ignored epsilon to simplify things. If I don't ignore epsilon, then that would be y here, and then it would be a Gaussian distribution, which depends on that, where the randomness would come from this epsilon.
why are you ignoring it?
Just to simplify my life for a second, but it wouldn't add too much extra. All right. Okay, so this is how we do prediction when we have input-output. These are our input-output data. So all that we did was a Bayesian version of a linear regression where on the W's weights we assume the Gaussian distribution. Yes?
What happened to the regularization of W?
That's here. So that's hidden in this because we already calculated the posterior distribution. Okay, so when we calculated this, the posterior distribution, it was the likelihood times the prior, and the prior was the regularization term. Other questions? Everyone is okay with this so far? Good. Okay, so we just did a linear regression with some prior distribution on the weights. So now the question is, what can we, in practice it won't work quite often, so what we want to do that to transform the observed inputs to a feature space first and do linear regression in that feature space, and we might get better accuracy there. So that's what we do in support vector machines. You have your inputs, you transform that to a reproducing kernel Hilbert space, and you do linear classification there. So we want to do the same thing here, and let phi denote this feature transformation. So for example, if I had two-dimensional inputs, x1, x2, then I might just create phi of x to be a feature transformation, like this. I just created one. Or you can use kernels where you define implicit features in such a way that, for example, you define a kernel and you know that this kernel will be an inner product between the feature transformation of the inputs in some abstract reproducing kernel Hilbert space. Okay, so what we need now is just this, that phi of x will be a feature transformation of my original inputs. Okay, and I want to do the same thing. So first, I have the input data, I transform that with the function phi, and I do the same linear Bayesian ridge regression there. Okay, so this is what happens now, that I introduce a new notation, phi of x will be just the transformed input vectors. And then my new prediction, instead of x transpose w, it will be phi x transpose w. So basically, whenever I had x, I just replace that with phi of x. And then I calculate the same things that we did before. So the predictive distribution will be the probability of phi of x transpose w given x star, the location where I want to predict, and the input. And then instead of x star transpose w bar, it will be phi of x star transpose w bar. And that will be the new mean. And the covariance matrix, instead of x star transpose A inverse x star, it will be phi of x star transpose A inverse phi of x star. Right? So we calculated w bar already in the previous slide. So wherever we had x, we will just have phi of x. Similarly with the covariance matrix. Wherever we had x, we just have phi of x there. All right, and that's how you do it if you have feature transformation. So the big problem here, though, is that this feature matrix now, it's a capital N times n-dimensional matrix. So I transformed the input points to capital N dimensional space. And that capital N might be very big. For example, if you use Gaussian kernel, then what would be that dimension? Infinite, right? So that's big enough. But generally, we like to use large dimensional feature spaces. And then when we do, this will be our prediction. In this prediction, we need to calculate W bar. In W bar, we need to calculate this inverse. It's a capital N times dimensional matrix. For example, if we have Gaussian kernel, then it would be an infinite times infinite matrix. In practice, that's difficult to invert. Questions? Are you following me? So this is how just you would do in theory, but if this feature dimension is big, in practice you cannot use this. All right, so here I just introduced some. So we want to find a solution to this problem. We calculated the predictive Gaussian distribution with mean and covariance, and now we are wondering how to use that in practice, because as we discussed, you would need to invert a feature dimension times feature dimension matrix, and if the feature dimension is huge, it's impossible. Okay, so some new notations. So phi star is just phi of x star. So the feature transformation in x star is the point where I want to calculate the predictive distribution. And f star, the predicted value of the function, it will be just phi star transpose w. And we proved that the distribution of this f star will be a Gaussian distribution with this mean and this covariance. So what we are going to do, okay, so this is what we proved so far. We are going to rewrite the mean and the covariance matrix to some form that in practice more useful. So the mean, we will get, this is the mean that we calculated. We just rewrite this in some other form, and this is the covariance we calculated. We try to rewrite this to another form to avoid these ugly matrix inversions.
Here, so if the feature map is going to an infinite dimensional space, then W is also, and that transpose means, so phi star transpose W means the inner product in that big Hilbert space, right?
Yes.
Okay.
Yes. So W, the dimension of W, is also capital M. All right. So here is the theorem that we will use. That we will prove that this distribution, this guy, can be rewritten into a longer but nicer form. Okay, so this will be the new mean, and this will be the new variance. I mean, new mean, so this is exactly the same mean that we had before, it just has a different expression. And the variance is exactly the same variance we had, it's just in another form. So why we like this form? Okay, so notation. So K is a matrix, phi transpose sigma times phi. You remember sigma was the covariance in the prior distribution on W. This is a n by n matrix where n is the number of instances. So this is a n by n matrix. N is an identity matrix with dimension n. Again, n is the number of instances. So as you can see, in this case, we just need to invert a n by n matrix where n is the number of instances. This phi transpose sigma phi will be a 1 by n matrix, so phi star right? And phi star transpose sigma times phi star is just a scalar. And again, here we just need to invert a n by n matrix where n is the number of instances. So that's the theorem. You shouldn't necessarily see immediately why this previous expression is equivalent to this. Yes?
Just intuitively, what does phi star transpose sigma p phi star mean? Because
Which one? This one?
yeah, for example, because sigma p is just a low low dimensional matrix, and phi star p potentially could be infinite dimensional. So I guess so my question is then, when you prove that, then you pretty much prove that the solution of that lies in the subspace, in the Hilbert space generated by the columns of phi?
Mm-hmm.
Okay.
Right. So what it means is just the inner product in the feature space, and we never need to. So it could be like a Gaussian kernel between x star and x, and wherever you see these phi transpose sigma phi, we can just replace that with the kernel function. So we don't need to calculate these guys.
What is going to be phi? You have phi star and then phi. What is phi? On the last line.
So phi is was the feature transformation of x.
And phi star?
And phi star is the feature transformation in x star, where you want to predict. Okay, so the point here is that in this Gaussian distribution, we just have quantities like phi transpose sigma times phi, which will be like the kernel value in Gaussian kernel. So you can just
Phi is the transformation of the capital X, right? The entire matrix, right?
once again.
Is phi the transformation of uppercase X? The matrix X? On the right hand side?
So phi is this matrix.
Okay, I see. Phi.
Okay. Oops. All right. So I know it's a bit complicated to follow, but I hope that if you printed out the slides, then you are still with me.
Again, how do you calculate K?
K is phi transpose sigma phi, and so let me define a kernel function like this. That kernel function between x and x tilde will be this phi transpose sigma phi. So it's just the inner product in this feature space where the feature transformation is defined by this quantity. So if you don't want to know these feature vectors explicitly, you can just say it's a Gaussian kernel, and we know because it's a Gaussian kernel that there's an abstract Hilbert space where there's a sigma for this and a phi for that, and it will be an inner product in that feature space. All right. So this is great in that sense that we never need to invert large feature dimensional matrices. We just need to define a kernel function, and then we are good. We just need to invert a matrix which has size n by n, where n is the number of instances. So Gaussian processes were very popular for a long time, till data sets got big. Because when we have big data sets, then it doesn't help us much, right? So for example, if I have 1 million data points, then I still need to invert a 1 million by 1 million matrix. Right? So you can choose either you want to invert a big matrix because of the feature dimension or a big matrix because of the number of instances. None of them sounds that good. So this is where there's an actively researched area what to do in this case when you have big data sets. And there are some tricks what people do, but they go in. So we cannot calculate this anymore. People just approximate this in some way. And if you are interested, I can send you some pointers how to do approximations in this case, but we are not going to discuss those details now. Okay, so what left is to prove that this mean is the same as this mean, and this covariance is the same as this covariance. And this is in the next two slides. I just want you to go home and look at those slides, and if you have questions, then ask me, but let's not spend more time on that. The details are there. The mean is very simple. You just need this lemma, where K is by definition this sigma transpose sigma phi, and you just need to prove that this expression is A times sigma times phi, where A is this guy here. So if you plug A here, then you will see that this is indeed the identity. And from this, you can prove that this expression here is this quantity, and that's what we needed to prove. The variance expression is very simple. You just need to use the matrix inversion lemma. The matrix inversion lemma says that for any matrix U, W, and V, and Z, this expression holds. Okay? And we just need to find the rules. So U will be, in our case, phi, W will be sigma inverse squared, V transpose will be phi transpose, and Z will be the inverse of the covariance matrix sigma. And then, if you plug these quantities here, then you will get this. So it's the Woodbury matrix inversion. Okay, so go home and check all the calculations. If you get stuck somewhere, then ask me. Okay, but at the end, this is what we get, which looks nice, that the distribution, predicted distribution at the point x star, given the training data, will have this value where you can replace all these expressions with kernels. Right, so for example, phi star transpose sigma phi will be just the kernel value between x star and all the training points. Right, so phi transpose sigma phi is a 1 times n matrix, and it's just the kernel value between x star and x1, x2, xn, and then you get this n-dimensional matrix. Yes, can you? Yep.
In this case, we actually need to calculate the features, right?
You can just use, so you can just say, let's start with the Gaussian distribution, or Gaussian kernel. Then I don't need to calculate the features, right? And I'm just defining, I'm just saying that so I start with the Gaussian kernel. And because I know that it's a proper kernel function, it means that there must exist a phi and a sigma and phi that this holds. And then you don't need to calculate phi. Yes?
So usually the kernel is just phi x transpose phi x. Over here we also have the variance of our prior. What does the choice of a kernel indicate about that prior? For example, we want that prior to be zero mean. So how do we choose our kernel to ensure?
Right, so you don't, what you do, that if you choose a Gaussian kernel, for example, the Gaussian kernel will have some parameters. And then you think of that parameters like those were these guys. But they are not necessarily true. So what you do, that you forget that there was a sigma here. You just start with, say, a Gaussian kernel, and that Gaussian kernel has some parameters, and you tune those parameters to be good for you. Or if you choose another kernel, like polynomial kernel, the polynomial kernel will have some parameters, and you tune those parameters.
So there's no intuition behind how a choice of a kernel affects our assumption about sigma b?
So it depends on the kernel. So for certain kernel, you can see that if you change the bandwidth parameter, for example, the Gaussian kernel, then it might indicate how it affects the weights. Yes?
So, I mean, what do you have to do here every time, and what do you have to do, what can you do once? And, I mean, so x and y.
So, right, so let's write that here. So what you have is that you start from a data set X, which is x1, x2, xn. And you have y, which is y1, y2, yn. And you choose a kernel, k, I don't know, x tilde. That's what you do. And then you plug these things there. So the probability of my prediction f star at the location x star, given the data x and y, will be this. So will be a Gaussian distribution in a scalar f star with mean that expression. So what's that expression? So we start with a 1 times n vector that has values k. It's between phi star and phi. So it's k x star x1 and k x star xn. That's a 1 by n vector. Times the inverse of that matrix, k plus sigma squared in. So what's k? K is a gram matrix of all between the kernel between all instances in the training data set. So the ij elements of this is k xi xj. And then I need to multiply, so I need to add sigma squared times the identity matrix to this matrix. I need to invert this and multiply with y, just my observations, y1, y2, yn.
So every prediction you have to do all this? Every time, there's no such thing as...
So this one, you can calculate this in advance, right? Because it just depends on the kernel of the input values. That's the gram matrix.
So the gram matrix does not include the new test pointer, but also the new...
Exactly. You don't... it's not in the gram matrix, right? It's an n by n matrix.
So it's O of n time to calculate for any point then?
Once again?
So it's O of n time for any point?
Yes. So for a new point, you need to calculate these guys, though. But not this.
And also in the variance?
And for the variance is the same, that you can calculate this gram matrix, and then these guys are the same as these guys. So you just need to multiply this pre-calculated gram matrix with this from left and right. Okay, so it's ON for each prediction. Yep.
Just a quick abstract question. So phi x, psi x, is the same as phi of sigma p a half of x? So can I push the sigma p a half inside p? It's my question.
Here?
Yeah. So
Sure. Yeah. Yeah.
Then it's there's no.
Mm-hmm.
Is there something we have to be careful of when we use kernels then? Because we're also kind of representing the covariances in this?
Right. So usually when you choose a kernel, it will have some parameters. And how you tune those parameters, that indeed affects this. It's just not always easy to see how it affects that.
But every kernel has
Some parameters somewhere, yeah.
It's
I mean,
silly.
Usually, right? So for example, you can always say that let the kernel, even linear kernel, you can say it's x transpose y, or you can say a constant times x transpose y, and then you can tune that constant. All right, so any question about this? Or so now you can implement this Gaussian process and you can do prediction. So let's see some results. So this was the data set, and the black curve is the GP, prediction. The dashed curve is the true function that generated the data, and these blue curves are the predicted covariances.
And what was the original?
The original, that was the original, this.
No, the original variance. So actually, it's not all.
Right, so this was the original function, and this was the data on that function. So if we increase the number of training points, then the point is that this variance will shrink. So you can see here.
So what you do is you pick a point on sine, and then you pick a random. No, you pick a point on x, and then you pick a point on the curve sine with variance, whatever, and mean the value sine.
So once again, so let's.
So you have this.
Oops. Yeah, I'm here.
You have the sine function, right?
Right.
For taking the training point, you take.
So for the training point, I sampled from the sine function and added some small noise. Those will be these.
And the small noise is according to the Gaussian, whatever you had?
Yeah.
Okay.
But in practice, even if it's not Gaussian, you can still fit and see how it works. Yeah.
So you started with the ECN framework, and then what do you mean by error bars?
Okay. So it's at each location, I predict a Gaussian distribution, and this is just the standard deviation. So that Gaussian distribution has a mean and some standard deviation. So that's what I mean on error bars. But because that's how people call it in machine learning, but we shouldn't call it error bars. Really, officially we should call this credibility interval, because that's what you predict about yourselves. They are not the true error bars in a sense, right? It's just the algorithm says, I believe the data point will be here in this tube. It doesn't mean that the data will be really there. It's just that's the algorithm's belief. But still, it can be useful sometimes, right? It's just we should know that the algorithm might make big mistakes. But at least it's capable of saying something about predicting this uncertainty. So that's why it's still Bayesian, right? And each location you predict a distribution, not just a mean value. Yes?
Back to what you said earlier about active learning. So where would you choose the points here? Or?
Right, so in active learning, for example, if I want to do regression, I want maybe my next point, I would say somewhere here where the variance is still big, and I want to decrease that variance. There are lots of different active learning heuristics, but one is that you want to get a sample at that location that minimizes the variance.
And it will minimize, what you're saying, it will minimize the variance regardless of your results?
Regardless of your observations, yes.
So maybe this is a dumb question, but how do you sample a function from that normal? Because, right, you can sample a point from it by plugging in the values, right? So how do you what if you wanted to sample an entire function? Or do you just...
So here I just did a grid thing, but so in practice, what you can do, multiple things. One, you can just predict in a point, then you will have n plus 1 points in your new training data. You calculate this thing again. You predict in a new point, that will be n plus second point, and you calculate the new thing again. The other thing you can do is that you can generalize this prediction actually. So you can replace this vector with now it's a 1 by n vector. You can replace this with a, say, 2 by n matrix, and then you would predict in 2 points. And right, so if you want to predict in n points, then you should put a m by n matrix here. The benefit of that you will just need to invert an n by n matrix. Okay. And this is just an example when I increase the noise. Then you can see that these variances are higher as well. And this is just another example.
So had we not kernelized, we would have gotten straight error bars and straight lines for.
So once again, I couldn't get.
Had we not kernelized our
So I used the kernel, but I don't remember what kernel I used here.
No, I'm asking, had we not kernelized our anything, had we used just the original data points,
Yeah, we just.
we would have gotten straight lines for the error bars and straight lines for our black code.
So if the question is if we don't use kernels, we just use.
We used the original form that we derived for F star.
So if we are not Bayesian, then it would just be linear regression, right?
No, but he's saying before you do it in feature space. Before you go to the feature space.
Right, so it's just a linear regression in the original space.
We could have still gotten the error bars, they would have just been straight lines.
Right, so it would be a linear regression and it would be straight lines, yes, indeed. Because in each location is still Gaussian, right, your prediction?
So even that is a Gaussian process, right? It's just not very.
Yes, yep. Yes?
Kernel is just.
So in linear regression, there's two errors. There's the Gaussian and then there's the error in your fit. So you're still going to have a tighter bars closer to where you have other points.
That's true.
Even in
Yep.
linear regression, you're not going to get constant error bands. Because if you have a whole lot of points in one spot, it gets tighter there.
Right, but that's true, but it would be still linear regression, right? So
Your fitted line,
Mhm.
I guess I don't know. What do you mean by linear error bars when we have it unlinear? You mean constantly? Is that what you mean?
No, just straight lines. Maybe they won't be constant, but
Okay, sorry.
all right, so that's for Gaussian processes. There are more slides. There's a completely other way to introduce Gaussian processes as well. So please look at those slides. But let's move on because for the topic for today is independent component analysis. What's the question? So, and please read those chapters in the Gaussian processes book as well. So that might help as well. And if you have any questions, then just please ask me. Okay, so now we change topic. And Gaussian process was a supervised learning, and we will discuss something that's unsupervised learning. And it will be somewhat related to principal component analysis. So here is the goal that we want to solve. Say you have two signals, S1 and S2. They are time series, okay? And someone mixed these two signals like this with these mixing coefficients A11, A12, A21, A22. And you only observe X12 and X22. Okay, so in this case, for example, this was S1T, this is S2T, and this is what you observe. And the goal is that just using these observations, nothing else, we want to estimate the original signals. Okay? So with independent component analysis, we are hoping to get something like this, where this would be the two estimated signals. All right, it kind of looks magical, right? In that sense that you just observe these two signals. How to estimate this?
Or you must have some understanding of the original thing.
Right, so we need to make some assumptions to do that, otherwise we cannot do it. And the assumptions we are going to make that the two signals are statistically independent from each other. And we will discuss that. So this is just formally the model. We observe x1t, x2t, which is a linear mixture of two signals s1t and s2t. We observe these quantities. We want to estimate the original signals, and we don't know the mixing matrix. We don't know the original signals either. Our goal is to estimate them.
You assume there is no noise in the observation?
No noise in the observation. It's just a linear mixture. But there are, because we want to start with the simplest case, but there are algorithms that can handle noisy observations as well. So here is an application that's called cocktail party problem. So imagine that there's a cocktail party where people talk independently from each other, and there are some microphones in the room. And the microphones would record the mixture of the people talking, and your goal is that just using the recordings, you want to estimate the original signals, right? So imagine that we had a weird cocktail party, and we have an emergency car in that cocktail party, and the TV is on.
Fast foods that have successfully made the long march to Asia, from Seoul to Singapore.
In this cocktail party, someone plays the violin. And there's a rock band too. Yeah, my favorite group. All right, and these microphones in the cocktail party, they record the mixed signals. All right. So our goal is that using these 4 microphones, we want to estimate the original signals. And how to do it? That's the question. So the input is a matrix. Let's say that each signal is sampled that I have, 500 long time series, okay? And then my input is a 4 times 500 matrix. Each row is a recording from these microphones. So if I just use PCA, because why not? I know that algorithm, then I can estimate the first PCA component, second PCA component, third PCA component, fourth PCA component. And then in this new coordinate system, I can see how these signals would look like. And then I can play those. So PCA doesn't do a good job to estimate the original signals, right? So this is what happens when I use independent component analysis. So I use for this so-called fast ICA algorithm, and these are the results. So this is this, right? So I cannot estimate the order, but I can still estimate the original sources quite well.
That have successfully made the long march to Asia, from Seoul to Singapore.
All right, so the question is how we did this. Any ideas? Yes, with that, and how would they? That's a good guess. Right, so how would we do that? So with ICA, but so if that's your task, that hey, here are these 4 mixed signals, estimate the original ones, what would you do? I know you would download the ICA toolbox and try, but say you don't have internet, you have to code something in MATLAB, then what should we do?
Try to somehow figure out what the most independent 4 things in our input are, and then separate those.
Right, so this is...
They have, each microphone has a fixed distance to each one of the sources.
We don't know those distances.
No, but it does have a fixed...
They do have fixed distance, so they don't move, for example.
So you can see what's the loudest or something.
Right, so loudest. So among these 4 microphones, so let's just assume that the loudness was the same for all. I can just normalize them to have the same, but I don't know. If you want, we don't need to make these assumptions. I just cannot really see how it could help us, but it might. But let's come back to this question. So the assumption was that these guys talk independently from each other. So these signals are independent. When I mix these signals, they will become dependent. And the mixing, you can think of this as a coordinate transformation. Right? So if I have 4 microphones, 4 independent signals, A mixing matrix is a 4x4 matrix. Let's assume that it's an invertible matrix for simplicity. And then what happens is that these new recordings will become dependent from each other. How can I measure dependence between signals?
Inner product.
Inner product.
Covariance.
Right, so I've heard covariance, and those are good in that sense that covariance matrix indeed gives me some kind of dependence, who is dependent with what, and the inner product is the same thing. But will it be enough? So I say I know the covariance of these guys. So imagine that in the mixing matrix, there's an orthonormal matrix as well. Then the covariance wouldn't change, right? So if I had S, that was my signal, and then I multiply this with the U orthonormal matrix, then the new covariance matrix would be ST transpose U transpose U ST. U was orthonormal, so this is identity. So I would just get the original covariance matrix. So if you had mixed signals and I mix them with the orthonormal matrix, they would be still mixed and dependent. So the point is that covariance matrix itself won't be enough. But it's a good start, at least. So how else can I measure dependence other than covariance? Right, statistical independence. So let's estimate the mutual information between these guys. And let's try to minimize mutual information. All right, so that will be our strategy. For now, before we go into the details, let's discuss the difference between PCA and ICA. So in PCA, we had a data matrix, and we wanted to factorize this data matrix to a product of two matrices in such a way that we would do a dimensionality reduction in a way that we would keep the most information about the data. So in this case, U can be the principal component vectors, and S were the new coordinates in those in the coordinate system of the PC vectors. And if the original dimension was n, then we had, say, m principal vectors when m was less than n. So this is how we compress the data. In the ICA problem we are going to consider now, again we have an input matrix, and we want to decompose this input matrix as a product of two matrices, just like with PCA, A times S. But here we don't want to do dimensional reduction. We assume that A is an n by n matrix and invertible. In PCA it was a n by m matrix, and they were just the principal components. Okay, so here we will be looking for a, we assume that A is invertible. We will be looking for an invertible matrix such that if I multiply my data matrix, my offset matrix, with the inverse of this, then I would get the original sources. Okay, so what we are going to do, yes?
So this would only work if the number of observations is the same as the number of...
Right, very good point. So in the case we are going to discuss, yes. But if you have more microphones than number of sources, you can be still good. If, say, you just have one microphone, lots of sources, then you will be in trouble. And that's very challenging. So there are algorithms that claim that they can do it, but usually they are not that good. So it's, for example, when you have just one microphone, it's called one microphone source separation, that problem. So you can Google, you will find many articles for that. The best one might be able to separate like 3 sources, and then that's it.
The problem that you may not know the actual number of sources in the environment.
Sure, so it could be even more difficult if I don't even know the number of sources, yes. So the issue is that I have less microphone, then I compress the data and I lose information. And that makes it very difficult to estimate the originals ones because I lost information.
Would speech recognition actually help? Because human recognition would allow us to, I mean, we are just one microphone, right? We can see, we can discern all of them.
Right, so that's a good point. So some algorithms indeed use that property that you have time series. So what we are going to discuss now, that those algorithms, they will not even know that we have time series data. So if you randomly shuffle in time, the algorithm would be still able to recover the sources. And actually these algorithms were pretty impressive, right? They didn't know that they have time series. If you randomly shuffle things in time, you would get the same performance. Okay, but that's a good point, and many algorithms actually use that property that you can exploit somehow that there's time structures. They might be smooth function in time. They might be say autoregressive processes in time. So there are algorithms that assume that the hidden sources are hidden Markov models that you mix. So indeed, that's a direction to exploit that, but we are not going to discuss them.
Does our hearing exploit like having 2 ears and head geometry to separate things?
Right.
It's not really relevant.
Yeah. So it's interesting that we humans are very good at this, right? That even with 1 ear, actually, we are able to separate sources.
I think that's because of the structure of our ear that is able to locate
Right, so it's because of the structure of the ear, but the point is that in algorithms, I don't know how to simulate that structure. So I don't know any algorithms that would be able to separate.
Unless you have precise locations of microphones.
Yeah, microphones don't have that structure.
Right, so if you know the locations of microphones, that could help too. Anyhow, so time is up. So this is where we are going to continue next time. So if you have questions, then please stay, and this is my office hours, so I can help answering them.